Now that we know the basics of the subatomic particles that make up every atom, we need to look a little bit at what makes them different and what we do know about them thus far, including things well, like fusion, fission, nuclear decay, and half-life. The first thing that comes to mind when I start thinking about confusing things is we all know that like particles repel one another's and opposites attract. So it explains why the nucleus would pull electrons forward, but why does the nucleus stay so tightly packed? Well, if it's mostly positive, well, it is positively charged because neutrons have no charge. There has to be another force there holding it in place. We call this the strong nuclear force, and it's what holds the center of an atom together at all times. But there are times when it's overcome, and we get a whole lot of energy because it is such a strong force that holds it together. So as we start to think about the nuclear physics and that nucleus of the atom possibly overcoming that strong force, you need to think about what makes it stable. And remember, there's unstable isotopes, and an isotope just has a different number of neutrons than what we consider a stable isotope. So there's a certain amount of neutrons and energy that's released when it becomes too stable or unstable. And then there's certain people that went into figuring this out, and not all of them really understood what it was. Maria and Marie Curie, that invented the X-ray, for instance, they didn't quite understand how radiation was affecting them. And even though they figured out how to get X-rays, they both died of radiation poisoning. Now, first up here, what we have when the nucleus of an atom becomes unstable is fission, because this is the most common that we can create on Earth, where it actually is breaking apart. So you have one nuclei splitting and becoming two. Now, there's a lot of things that can split it. This model down here is showing a slow neutron, so it's a neutron-induced fission, but it causes it to split. And that split will allow it then, they'll form a more normal or a more stable nuclei. So it's no longer going to be uranium because you divide the amount of, or you would break up the amount of protons and neutrons, so you would get something else out of this. Okay? And it usually releases certain amounts of neutrons itself. So a neutron might cause it, but it would release some itself. It's a tremendous amount of energy. In fact, this is where we get nuclear bombs from. And let's take another look at that. So the reason we use this example of neutrons or uranium is because if you look at this, a neutron can create a chain reaction within uranium because uranium's not made of a single element, or a chunk of uranium would not be made of one uranium atom. It would be made of a bunch of uranium atoms. So we just had to create basically an implosion that created enough of a reaction of a slow-moving neutron to start fission. Once it starts, fission releases energy itself and neutrons itself, which can cause this to cascade and happen more and more and more and more. Remember, we're getting a large amount of energy released each time one of those uranium atoms splits in fusion, because that strong force has to be overcome, and there's a lot of energy that snaps out of it, kind of. If you'll notice this formula down here, this is looking at more of a reaction. So it is becoming other elements as it moves along as well, but sometimes they're not stable yet either, and it'll keep cascading. And so it can get out of control very quickly and multiply, and that's why the atomic bomb is so powerful. But fission is not the most powerful thing. The most powerful, where the most energy, would be fusion, where you're not breaking apart a nuclei, you're actually fusing, thus fusion, you're putting the two together. And so this happens all the time in our sun. It's actually what powers our sun. Our sun is constantly converting hydrogen into helium. Now it takes a tremendous amount of pressure, that's why it only happens in the core of the sun, and it needs a really high temperature, excess of, this is 40 million degrees Celsius. Let's take a look at that reaction though. Now, in the very core of our sun, we have hydrogen. and hydrogen is going to be fused together. Now, if you know anything about hydrogen, it's the smallest, or it's the very first atom that we have because it is only one proton. In fact, it doesn't even need any neutrons in there. It's just a single proton. It might have an electron to make it balanced, so it's not an ion, but a lot of times when we're talking about in the sun, we're assuming that most of the electrons got ripped off, and so we're just looking at these 4 hydrogen nucleuses, so 4 protons really. And what happens is they're then going to fuse together. But they don't then form 2 helium. No, you would only get 1 helium. And a helium atom is made of 2 protons and 2 neutrons. And so a lot of times they do that little NO for neutron, right? And so this is going to make our helium atom, that's He, right? And so you might be thinking, well, how did I take 4 protons and get it down to just 2 protons and 2 neutrons? Well, the thing is, there's a level beyond what we can actually play around with of subatomic particles of protons, neutrons, and electrons called quarks. And those quarks basically, or what we believe, most of it's theoretical, is making up these particles. And so in those, the quarks get rearranged in this strong force so that some of these actually emerge as neutrons and some as protons, so that we get a new stable element, helium. Helium is actually very stable. And because of that, it's one of the things that gets shot out. But it's not all that happens. In this fusion, we also get a tremendous amount of energy. Woo! And that's actually what we see as light. So we end up getting this tremendous amount of energy coming out of it, and it's what powers our sun. Because it's able to continually force these hydrogen together, all 4 of them, to make 1 helium, we get a ton of energy that comes with it. So I guess I need my little plus sign there, showing that we get tremendous amounts of energy with it. And that's really what is powering our sun, is fusion. The fusion of 4 hydrogen nuclei into a single helium nuclei. Now you might be asking, how do we know that it's hydrogen and helium? Well, because of the energy that it gives off. And we're going to talk about that in our next video. So, interestingly enough, with all that we know about nuclear energy and the massive amount of energy that it releases, we don't actually capture that energy per se. We capture it a little bit, but only in water. We basically use it to heat up water when we have our nuclear power plants. And it creates that steam, which still runs a turbine, a steam turbine. And that's actually how we use nuclear power, is we have things like uranium that are giving off lots of this radiation anyway. And as we break it down, we use that energy just to heat up water. And remember, it's going through fission, and then it'll turn the turbine, cools back down, and we send it back through. It radiates the water, which is also why there's so much nuclear waste involved. But that's what powers a lot of our nation at the moment. Not the most efficient use of it, but easy to get.